So in the last video, we showed that r cross v, the velocity vector, is equal to a vector that doesn't depend on time. This characterizes the motion of an object in a plane. So the plane is always the same. Let's figure out what this vector is. So let's write the position vector in radial coordinates, in polar coordinates, r theta. So this looks like some distance and some r hat. And let's evaluate dr by dt. So we'll take derivatives of this first, right? It's a chain rule, so we have dr by dt times the unit vector plus this times the derivative of that, right? How does the unit vector change with time? Well, we can see that if we're going in a circle, then that unit vector is changing with time, right? It's pointing, say, that way initially, that's the r hat, let's say, then we're going in a circle, then it's going to go that way, r hat, and so on will go around. It's changing at the rate of the angular speed. So this becomes dr by dt, r hat, plus r times d theta by dt, which is the angular speed. But it's pointing in the direction of the angular direction, so there's a theta dot. So dr hat by dt is d theta by dt. That's the magnitude, but its direction is in the angular direction, in the theta hat direction, where right, that's the radial direction, and then that's the theta hat direction. So this would be our hat, theta hat, something like that. Okay, so r cross dr by dt can now be evaluated because we have dr by dt. So this becomes, so this is h, so we want to see what h is. So we have r hat in r theta coordinates cross, let's call dr by dt just r dot times r hat plus r, again, d theta by dt will do theta dot, theta hat, and this is r squared theta dot, right, because the cross product here is 0 because we have r hat cross r hat. So we have r squared theta dot times a unit vector, which is the result of r hat cross theta hat, and that has to be out of the plane in which the coordinates we're using is r and theta, right? So it has to be perpendicular to that. So we have r squared theta dot, I don't know, let's use some k hat for that. And so this is our vector, and it has a magnitude, which is r squared theta dot. So let's get a sense of what this is. Well, we can sort of see dimensionally that this is an area divided by a time. So it's the rate of change of an area. So if we imagine that an object is going in a circle, well, it's not quite a circle, right? So we have some initial position r, and then we're going around, we're rotating, let's say, but we also can move in the radial direction. So we can move in the radial and theta direction. So we move out, let's move out a little bit in the r hat, in the r direction, in the radial direction, sorry, as well, but we're changing the angle by a little bit as well. So let's do a d theta, and this is an r plus dr quantity. Maybe we should use symbols, a delta symbol here, but whatever. We're going to think about this in the limit that these quantities go to 0. So, right, so we've changed the area by an amount here, right? That's that area. That's the area we're considering, and this is like, well, r d theta. It's really, there's an r. That's not quite r d theta, but in the limit that dr goes to 0, well, so the change in the area, and delta A is equal to the infinitesimally small area that's here as these things go to 0 is represented by this delta A. It's this is kind of like a triangle. One side, this side times that side divided by 2, and so we sort of have something like this: r plus dr times this side r d theta, and we divide that by 2. And so, and that is, we'll ignore quantities that are second order, dr d theta, so this is approximately just r squared d theta over 2. And so in the limit that these quantities, these infinitesimals, really we should do delta r and delta theta, and this is a delta theta. As we think of an infinitesimal time dt, right, then we have an exact relationship where this becomes a dA equals r squared d theta over 2, and therefore we get that the rate of change of the area, dA by dt, is r squared d theta by dt over 2, and so that's just theta dot. So that's really h over 2 in terms of the magnitude. So the rate at which the area changes is constant, and this comes from the fact that we have a force that is along this line.